Up from where we left in class. So this is what you have to do. So we have the information here. We get 28 black tokens and 20 white, 28, 12 white tokens. And the player draws one and puts it back in the bag, so makes this independent because the total doesn't change it. It doesn't change since you're replacing it, right? So the first event does not affect the second event and so forth. So based on that, what's the probability that, look at my bag, this is what I have inside, and that get a white? Well, looking at that bag and without doing anything, not performing an experiment, I know that the probability of getting a white is 12 out of 40 because there's a total of 40. Now, based on the information given, which I wrote over here because that thing didn't fit on my screen, they did an experiment. They drew tokens, put them back, tokens, put them back. They did that 10 times. That was the experiment right here. So based on this experiment, what was the probability of getting white? Well, on the last 10 tries, how many whites came out? 1, 2, 3, 4. So the probability of white in the experiment was 4 out of 10. Okay, so nothing. So C. Now Henry says that he wants this probability, and I'm going to simplify this. If I divide that by 4, I get 3, right, or 3 over 10. Right? So we can tell clearly that in the experiment, we got more white tokens than expected. We were expecting 3 out of 10, we got 4 out of 10. Now he says that Henry says, but by taking some of these tokens, the black tokens out, he can make the theoretical probability of 310 be the same as the experimental probability, which was 4 over 10. So let's see how many of these tokens we have to take out. So right now, we want, this is the experimental, right? This is the theoretical. He wants to have the theoretical, which is 12 out of 40. Right? In theory, to get a white token, you had a 12 out of 40 chance, but he wants that to equal this. Now, notice that these are, we can think of equivalent fractions, right? So we want to remove black tokens. So this, which represents the number of white tokens, will stay the same. So 12, and if you think of equivalent fractions, 12 to become 4, I divide by 3, right? So I want to change the total here. So if I remove, let's say I remove 8 black tokens. So if I remove 8 black tokens, I would have 20 black and 12 white, right? And the probability would be 12 out of 32. Now, would 32 work? Well, 32 doesn't work because if I take 32 and divide that by 3, it's not going to give me 10. So I need to figure out what number, what total here can I make, divide by 3 to give me 10. So that has to be 30, right? So if I have to be 30, so I have to change the total number of tokens from 40 to 30. And how can I do that? Well, one way of me doing it is to remove, and they said remove black tokens. So if I have 40 tokens right now and I want to make it to 30, I can remove 10 here, 10 black tokens. So if I remove 10 black tokens, I am left with 18 black tokens. Now let's see if that works. So that means if I remove from the original 28, I remove 10 black tokens, I'll have 28 black. And then I'll have the whites I didn't touch. So I'll have a total of 30 tokens. Now let's calculate the probability of that. So if I had this scenario now, I would have the probability of getting a white token would be 12 out of, and if you add these two, you get 30, 12 out of 30. Is that an equivalent fraction as 4 over 10? Well, 12 divided by 3 is 4, and 30 divided by 3 is 10, so they are equivalent. So how many black tokens would I have to remove? I have to remove 10 of them. Okay, and if I remove 10 of them, right, and then if I remove 10 of them, my theoretical probability, right, would be 12 out of 30, which is the same thing. If I divide this by 3, I get 4. I divide this by 3, I get 10, which is the same as the experimental probability of 4 out of 10. Okay? Now, on the same token, they're asking us to do kind of the reverse, right? So again, the probability of getting a white token, right? I'm doing letter D, by the way. The theoretical probability of getting a white token, as it is right now, right, is 28 out of 40. 28 y out of 40. Now, in this case, he's saying, how do I make 28 out of 40 be the same as the experimental probability, which is 4 out of 10? How do I make this that? And he wants to do that by adding white tokens. So let me take this back. Right. So how do I do that? Well, if I have 12 white right now and 28 black, if I add, and obviously we want to add something that's going to divide and give me an answer of 4, and likewise the same number divided give me an answer of 10. How do I do that? Okay, tell me if we can do that. Well, if I add, and let's play around with the numbers here. If I add 4 to the white, so if I have 28 black tokens, and let's say I add 4 to the white tokens, so a total of 12, I'm going to have 16 white tokens. Right, so if I add, and that would give me 44 total. Well, let's try that. I would have 16, and 16, if I divide by 4, it does give me 4. But if I take the bottom, right, 44, because my total change, I added 4 more, I have 4 more, and divide that by 4, it's going to give me 11. It's not going to give me the, what do you call it, the experimental probability of 410, which is what we're trying to match. We're trying to match the theoretical with the experimental. Now, what if I added, I don't know, instead of 4, let's say I added 8. If I added 8, right, I would have 20 white. So the probability would be 20. And the total, because I added 8, is now 48. I can't make an equivalent fraction out of that. Well, 20 divided by 5 is 4, but 48 divided by 5 is not 10, it's 4.8. So notice that this is not going to work. Okay, so by adding white tokens to this so that I can get this initial theoretical probability to match the experimental probability, doesn't really work. Let's see, make this a little bigger because I can't see. Now this you can fill in with this. You can estimate the probability of an event by performing an experiment. The experimental probability of an event is the ratio number of times that the event occurs. So something has to happen. It says occur, not may occur, but occurs. The more trials performed, the more accurate your estimate will be. Okay, your experimental will always approach the value of your theoretical the more you do it. Okay, so an example of this is that if you flip a coin 10 times, you can get 7 heads and 3 tails. While we know that flipping a coin is half and half, so in 10 times we would expect 5 heads and 5 tails, right? But you did the experiment, you got 7 heads and 3 tails. You got a little bit more on the heads. But again, if I told you to flip this coin 1,000 times, that initial 7 heads and 3 tails will probably be, like I said, the more you do it, now we're probably, I don't know, I'm making this up, but it could be 590 heads and 510 tails. And then let's say you added and you did it 1,000,000 times or 10,000,000 times, right? That probability would get closer. These two numbers will be closer and closer to 50-50. Okay, so the more you do it, right? So if you do it only 5 times, and let me give you an example here. If you only flip the coin 5 times, I mean, it's very possible you can get heads, 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 and heads. And there goes your 50-50, right? Your 50-50 theoretical that you were expecting, right? So, but if you do the 6th time, maybe a head comes out. If you do it 7 times, a head comes out. The 8th time, tails comes out, and the heads. And then slowly, the heads start coming out, and this half and half, right, starts becoming more real. Okay. So an experiment consisting of a spinner, they actually did it. It came out red 7 times, blue 8, green 5. So there's a total of 20. So the experiment was done 20 times. Write your answers a fraction, decimal, percent. God, I hope you just wrote 1. That's fine. I should have said something. Lands on blue, 8 out of 20. If you want to change it to a percent, multiply by 5, so that's 40%. Right? 0.4. Oh, I'll do it. Does not land on blue. Not on blue would be the red and the green, so that's 12 out of 20. Multiply by 5, you get 60%. 0.6. Does not land on green would be red and blue, so that's 15 out of 20. 75%. 0.75. Lands on red would be 7 out of 20, which is 35%, or 0.35. And then does not land on red would be blue and green, which is 13 out of 20, which is 65%, or 0.65. Okay. Again, another one. The math grade of 28 randomly select the students received. Use the graph to find the experimental. So what was the experiment? The experiment was that students taking the test. Right, as a fraction, decimal, percent. What's the probability that a kid got a C in the class? Well, let's find the total first. So that's 4, that's 12, that's 10, and that's 2. So we have 8. There's 28 students in total. Probability that a student picked a random and got a C, let me write this a little bigger, would be 10 out of 28. And I'm going to leave it. Well, I mean, if you have a calculator, you can divide. A B or better would be anybody who got B and A, so that would be 16 out of 28. Earned an A in the class would be 4 out of 28. C or lower would be C and D, would be 12 out of 28. And then did not earn an A would be all the kids who got a B, a C, or a D. So 12, 22, 22, and 2, 24 out of 28. The student is at least 160, so they took the measurements. If you pick a kid and write randomly, what's the probability that he's at least 160? At least 160 would be this group, right? Kids who are here, here, and here. So we have, well, total, so at least 160 centimeters would be 8, 5, and 1 would be 14 out of 23. Less than 165 centimeters would be this group, and this group, which we have 17 out of 23. Between 165 and 70 would be this group right here. That's just 5 out of 23. And then between 155, okay, 155 and 170 all the way up to here. It would be these 3 groups. It would be 7, 8, and 5, which would be 20 out of 23. Pretty straightforward, right? Let's see. We can use experimental probability to make predictions, right? So let's see what this is. We selected 100 people out of 2,000 in the high school, and we asked them about plans for after graduation. What's the probability that a randomly selected student plans to go to community college? Well, community college, so in the survey, 24 out of 100. You can simplify that. 12 out of 50, 6 out of 25. What's the probability that a random student selected plans to go to trade school? Where's trade school? 15 out of 100. 3 out of 20. Based on the results, how many of the 2,000 students would you expect to go to community college? Well, community college we had 6 out of 25, or 24 of our 100. So use a simplified version. 6 out of 25 said, I want to go to community college. But if you take that percentage and multiply that by 2,000, right, we can simplify 2,000 divided by 25 equals times 6. We're going to get 480 students will go to community. We can predict. How many would you expect to go to four-year college? Well, four-year college, 43 out of the 100 said, I want to go to four-year college. So 43%. No, 43 out of 100. Yeah, 43 out of 100. Multiply that by 22,000 students. We can cancel this. And then 20 times, we get 866. We can expect to go to a community college. All right. On a quiz with 15 questions, Craig got 12 questions correct. There's your experiment. He took the test. Right? If a question was chosen at random, what's the experimental probability that he got the question correct? Well, it would be P of correct. Right? It would be, there's a 12 out of 15 chance that you picked one of the questions he got correct. If he takes a second quiz, but this time has 60 questions, what's the number of questions we think he would get correct using the experimental probability? Well, if this continues, right, 12 out of 15, multiply that by 60, and a question with 60 questions, he's probably going to get about 48 correct. Okay. 3, same thing. There's 800 light bulbs, and we find out that 796 have no defects. So the experiment was, out of the line in the factory, pull out 800 light bulbs. Okay. So what's the experimental probability that the light bulb chosen has no defects? Well, in our experiment, we found that 796 out of 800 has no defects. If the manufacturer sends a shipment of 2,400 light bulbs, how many of those would not have the same, not have any defects? So if you take 696 and you divide it by 800, it's telling you, that 0.995, so 99.5% of our light bulbs had no defects. So out of the 2,400, we're also going to expect that 99.5% of those light bulbs have no defects. So you got two choices. You can either multiply by 99.5 or 0.995, or you can multiply the fraction, the original fraction, 796 over 800 times 2,400. It's really up to you, whichever makes it easier for you. So times 2,400, 2,388 should not have any defects. Okay. 4, Toyota inspects 15 electric hybrid motors for its Prius model, and find out that 1,497 did not have any defects. So again, that's the experiment. So in your experiment, what do we call no defects? Right. So we actually inspected 1,500 cars, and 1,497 were good. So that same ratio, right? So again, let me just take a moment to divide that to give you the percentage. So Toyota has a 0.998, what do you call, no defect rate. So 99.8% of all of its motors had no defect. So we can expect out of the 35,000 motors in the warehouse in California also has a 99.8 no defect success. So choose, you can multiply as a fraction or as a decimal, whichever one you want. So no defects, right? Out of 35,000, because that's what we're doing, right? It would be 1,000. Again, I'm going to multiply because I have this and I'm too lazy to write it as a fraction. I can 0.998 times 35,000. So how many engines will be really, okay, times 3,500. We can expect that 34,930. Sorry, I don't know why I put up the money sign. Motors will have no defects. So it still leaves with 70 motors with defects. Right? So, what do you call it? That's quite a chunk. Yeah, that's it. Right? Pretty straightforward.